All right, the last thing we're going to talk about in this section is net change. Okay, and we've hinted on this before when we were talking about definite integrals. Okay, so when we were first talking about it, we were talking about how the integral and the derivative are related. And we had something like this, right? Okay, and we also talked about how this definite integral is the net change in y. So the net change in y is the integral of the rate of change. All right, and let me be a little bit clearer. Y is equal to f of x, capital F of x, okay? So let's draw a quick sketch about what that net change means. So let's say we had a function on a closed interval a to b, and it was our f of x function, and we're going from a to b, okay? The net change is how much we change from point A to point B. All right, so this is your f of A, and this is your f of B. So this distance right here, that's your net change. And notice in this example, whatever this is, if this were to, represent a position function or something, we travel more than that, right? We travel much more than that. So the net change isn't so much about where our graph is going or where our graph has been, it's where we started and the difference between where we ended. Okay, so let's look at an example, and we're going to find the net change, and we're going to compare that to the distance traveled. So let's define a velocity function to be t squared plus 3t minus 4, and we're going to define that for the first 3 seconds, 0 to 3. And in this case, let's talk about your units. It's in terms of meters per second. Okay? So the first thing we're going to do is we're going to find the displacement. And the displacement is the net change. So a little vocab for you. So again, the displacement is the net change. And it's the net change in position. So what's the difference between where we started and where we ended up? That's the displacement. Okay, so in our case, we have, our time limits 0 to 3. And so the displacement is going to be s of 3, so that's our ending point, minus s of 0, where we start. So that's what the displacement is. So how are we going to find it? Well, remember that s prime of t, the derivative of the position function, is exactly the velocity function, okay? So here's our train of thought. We're going to look at, let's see, if we want to end up here, s of 3 minus s of 0, that's the displacement, right? Well, according to what we just looked at, s of 3 minus s of 0, we can take the limits of integration from 0 to 3, s prime of x. Okay, so the limits of integration are going to go from 0 to 3, s prime t, dt. And then what's S prime of t, it's the velocity function. So let's make that substitution. T squared plus 3t minus 4. All right. So we have to find this, and we're done with part A. So let's go ahead and take the integral. Okay. And we're going to plug in 3 and the 0. All right, so when we plug in 3, we're going to get 3 cubed divided by 3, which is like 3 squared, plus 3 halves, 3 squared. So 3 times 9 is 27. And then minus 4 times 3 is minus 12. And then when we subtract, when we plug in the 0, we're just going to get 0. Okay, so this is what we're looking at. Okay, so we can simplify this, multiply your fractions, top and bottom by 2 to get that common denominator. So we get something like 21 over 2, which is like 10.5. And then what are the units? What's the displacement now? It's meters. So we're looking at 10.5 meters. Okay, so there you go. So now that we have the displacement, we're going to actually figure out how much this object traveled, right? So we have this position function. I'm not sure what it looks like, but similar to something we just did. What should we do? Oh, maybe something like this. All right, I don't know. So just a quick sketch, and it's actually degree 4. But here would be S of 0, and let's say S of 3 is here. Okay, and so again, just a sketch. So the distance between the starting and the ending points, this is your displacement. And what we're going to find next is the total distance traveled. And the distance traveled is the length of that curve. The distance traveled is going to be the length of that curve. And we know that the length of that curve is going to be really difficult. But luckily, distance traveled is the area of the velocity. So let's draw S prime, or the velocity. It is t squared plus 3t minus 4. Okay, let's do a quick sketch. I'm going to sketch it using the zeros, the x-intercepts. Our zero factor property. So we have zeros at -4 and 1. And I'm going to use the fact that it's a parabola with a positive leading coefficient. So we're going to have a happy face, okay? All right, so -4 to 1. So we have something like this, right? And then this is our velocity. So we went from 0 to 3, right? Whatever that happens to be. Just a quick sketch again. And the integral from 0 to 3 was this area and this area. And we want to find their difference. Okay, so if this is A1, it's going to be negative. And if this is A2, that area is positive, right? Areas below the x-axis is negative, areas above are positive. So this expression A2 minus A1, that's the displacement. Let's write out all the words. That's the net change, We're calling that the net change right now. And that's exactly what we just found. 0 to 3 of s prime of t. Okay? So it's s of 3 minus s of 0. Okay, so if we wanted to get the total distance traveled, instead of subtracting the two areas, we'd want to have a running total. Okay? So we're going to have to add the distances instead. All right, so how are we going to do that? How are we going to do that? Well, when we take the integral, we don't really know where the area is negative and where the area is positive. Okay, we just know that the net change, what the net change is. So here's going to be our strategy. We're going to have the velocity curve, right? This is our velocity, just like before. And if we take the integral from 0 to 3, it's going to do the subtraction, unfortunately. So what we're going to do is we're going to break it up. And we're going to break it up to where the function is positive and where the velocity function is negative. So rather than doing v of t right here, where v of t is negative here. So what we're going to do is, how can we make v of t positive so it goes above the x-axis so we can count the area as positive? So then we're adding the two areas. So how can we make that change? Well, how do we make a negative number a positive number? We have to take the absolute value, okay? So net change, displacement, we take the normal definite integral. If we want the total distance traveled, not the displacement, but the total distance traveled, we have to look at the absolute value of A1 plus the absolute value of A2. Okay, so the distance traveled is the integral from 0 to 3. And now we're going to take the absolute value of the velocity function. Okay, so we're going to have to figure out where the function is positive and where the function is negative. And we kind of did that by looking at a graph. So, we know how to figure out if a function is positive or negative. We find the critical numbers and we use test points, or we look at the graph. And then this time we did the graph. Our critical numbers were -4 and, what was it? And 1. Okay, and just given the nature of a parabola, we knew it was going to look like this. So if we're talking about the absolute value of this function, we've found the critical numbers, we graphed, or we could use test points, so we know where it's positive and negative. All right, and it's negative between 0 and 1. All right, so instead of v of t, the absolute value at that point will be the opposite of v of t. So the opposite of t squared plus 3t minus 4. All right, because we're taking the absolute value when the velocity is negative. All right, and how we take the absolute value of a negative number, it's the opposite of the negative number. Okay, so for 0 less than or equal to t less than 1. And then after 1, the normal velocity function is positive. Okay, so we're dividing up our interval, and luckily we can introduce that midpoint between 0 and 3 and add an integral. So remember, this is one of our properties. So we can go make one integral from 0 to 1 and then another integral from 1 to 3. So from 0 to 1, it's going to be the negative velocity function. Okay, and then from 1 to 3, it'll be the normal function. Okay, So there you go. So we kind of do twice the work, right? But that's okay. So let's take the integral. All right, evaluate it from 0 to 1. Do the same thing over yonder. Be the same integral. And then evaluate that from 1 to 3. Okay? And now we're going to plug everything in and see what happens. Okay, so luckily we have a 0, so we get to luck out a little bit in this case. So it's going to be negative 1/3 plus 3/2 minus 4. Okay, and then, minus 0 when we plug in the 0. I'm not going to write it though. Plus, and then parentheses are important. Let's plug in the 3. 1/3 t cubed, 1/3 times, I'm going to do some shortcuts, 1/3 times 3 cubed, cancel 3, we're getting 3 squared, plus 3/2 3 squared, so 9 times 3 is 27. And then we're here, minus 4 times 3 is 12. Okay? And then we're going to subtract the 1. So 1/3 plus 3/2 minus 4. Did I get it? Okay. Yeah. And then if this was a minus sign by chance, we would need, giant parentheses around this. But since it's a plus, we don't have to worry too much about it. Oh my goodness. So what are we going to have to do? So I'm going to just try to simplify this a little bit. Did you guys see that these two expressions are the same? So I can kind of treat them as a coefficient. -1, just do the operation on the coefficient. I'm sorry, treat it, as a variable. Makes it just a little bit easier, not much. All right, now I can distribute that -2. One way to simplify it, there's lots of ways. You guys can just go left to right too. That's fine. Okay, so I'm going to distribute the -2. It'll cancel in that case. Okay. All right, and then -3 plus 8 is 5, plus 9 is 14, minus 12 is 2. And then we have our fractions to worry about. Okay, so we can, find the common denominator. It's 6. Do a little arithmetic. And we get 89/6. And then, normally with these displacement and distances and stuff like that, it's okay to go to a decimal. It's a little bit easier to understand the distance, right? If your friend said my house is 89/6 miles away, you'd be like, what are you talking about? But 14.8 miles, you're like, oh, okay, I get that. Okay, so what have we learned? Displacement, normal, definite, integral. All right, displacement, a to b of the velocity function is equal to s of b, the starting point, or the ending point minus the starting point. That's displacement. Total distance of an object traveling is the absolute value. You got to figure out where your velocity is positive and negative. Create that piecewise function. A little bit more involved to find the total distance, for sure.